Okay, good morning, everyone. Today we're going to start module 2, chemistry of nutrients. So this is the one, chemistry of sugars 1. This is content. Although basically we're going to introduce the concept of carbohydrate, the chemistry of carbohydrate. First of all, the classification of carbohydrate. We're going to talk about the monosaccharide and their classes, disaccharides and an example, oligosaccharide, polysaccharide, and then the basic concepts on the structure of glucose, isomerism, optical activity. Carbohydrates, what is carbohydrate? Carbohydrate, here represented by C. We usually see the carbohydrate, that is basically the general formula carbohydrate. Not like that, the formula is CN and when you have an equal 3, there's some time simply the update is carbohydrate. So carbohydrates is the most abundant organic molecule or biomolecule in nature. Why believe this is the by definition, when you define carbohydrate, there's a compound containing carbon, hydrogen, and with this that in a much more classical level, we define carbohydrate as just a hydrate of carbon. Of course, when we say hydrate of carbon, there might be other, because there are other compounds that they are also fall within this compound. But specifically, when we say they are polyhydroxyaldehyde, polyhydroxy simply means aldehyde and ketone that contain a lot of hydrogen. Well, of course, we can also have it. But classically, this information will give an idea of what's carbohydrates. Just like the biomolecule, other biomolecules, because how to even though we can get expecting with the because that they are not polymer. But protein are polymer acids. Nucleic acid are polymer. So nucleic acid come out with this class. So carbohydrate also are polymers of sugar, simply sugar. Saccharide from the word saccharide, which is a Latin word from the sweet person of the sugar. Here we have monosaccharide as one sugar, mono saccharide sugar. So glucose is the most important carbohydrate. See what is the glucose and others. Glucose represents the most important. So by classification, we say carbohydrates are classified based on the number of individual sugars that comes together. Number one, we have monosaccharide. What I say, we have monosaccharide, we have disaccharide, mono 1, di 2, oligo, when you have about 3 to 10, and then you have poly, when you have up to the. Now let's look at monosaccharide. The simplest group of carbohydrate, often referred as simple sugar. This cannot be further hydrolyzed to a simpler, a much more simpler form. They are classified on a number of bases. Number one, the basis of functional group, they are classified into two. We have aldehyde, those that contain an aldehyde, and go into ketone group. So those that contain an aldehyde, they are called aldoses, while those that contain a ketone functional group, they are called ketoses. We all know what is an aldehyde, what is a ketone from the classical chemistry, definitely. And on the basis also of the number of carbon atoms, starting with the two, the simplest one is contain 3 carbon. They are called trioses. Those with 4 carbon, they are called tetroses. Those with 5 carbon are called pentoses, just as we explained in the case about discussing nucleic acid, where we mentioned a sugar that is from the component of nucleic acid. Ribose sugar, we say pentose sugar, sugar. We also have hexoses, 6, and the highest we have seen is hexoses. Although it's possible we can have more than that. So let's just look at some example of these sugars. I'm looking at the structure and the difference based on the structure. The structure of aldoses here, we have a 3 carbon sugar. We only have 1, which is glyceraldehyde. 4 carbon, we have erythros and threose. 5 carbon, we have octavo, ribose, arabinose, xylose, lysose. 6 carbon, we have octane. 1, 2, 3, 4, 5, 6, 7, 8. 8 of them. But there is what we call asymmetric carbon. I think we talked about asymmetric carbon. I'm trying to remember where we're supposed to discuss the asymmetric carbon. So, in any case, this asymmetric carbon or asymmetric center can be determined on each. For example, let's look at the 3 carbon. The one in red, we can see they have 3 carbons here. Which of these carbon is an asymmetric? The carbon in which the 4 group attached to each differs. Of course, number 1, no, we have only even 3 group, rather. So it's even incomplete. This initial of this is the orbital is incomplete as a development. So the second carbon, we can see that the carbonyl group attached to 1. I think that is this thing. We have a carbonyl group here, which is different from the hydrogen attached here. Here is hydroxyl group, while here is also different from. It's also different from the other component. So we can see this residue is different from this residue, different from this residue, as well as different from this residue. So this carbon is called an asymmetric carbon, chiral carbon. This carbon determines the number of isomers this molecule can produce. So a molecule with only 1, so the formula is equal to 2 raised to the power of n. N is the number of the asymmetric carbon. So if N equals 1, is equals the number of the isomers this can produce is only 2. So we have this D-glyceraldehyde. You can see D attached here in all the names. There is another glyceraldehyde that is L-glyceraldehyde. We are going to see YDYL. Although I already said it, it is D because the OH group is attached to the by the right side. While when it is to the left side, it is called L-glyceraldehyde. So why D only put here is because the D are the most common, the one found in biological system, while L is rarely found in biological system. And the enzymes that involved in even metabolizing this, they actually metabolize the D form instead of the L form. So likewise, in the case of 4 carbon, when you substitute the chiral carbon is 2, when you put 4, you're going to have a 4. So 2 of them, they are in D, they are called erythros and threos, while the other ones are L-erythros and L-threos. Likewise, in the case of 5 carbon, we also have 8. The 4 of them, we have D-ribose, D-araginose, D-xylose, and D-lysose, while the L form of these ones make up the 4. So in the case of 6 carbon, we have 16. 8 of them are D, which include D-allose, D-altrose, D-glucose. Now we will see where the glucose comes from. So glucose is just one of the sugar out of all these ones. We have D-mannose, D-glucose, D-idose, D-galactose, and D-talose. So in the discussion, we will see more about the structure of D-glucose because it is the most common one being used by the. Okay, in ketosis, we also have the dihydroxyacetone. So it doesn't have a chiral or a symmetric center. We have D-erythrulose. In 5 carbon, we only have 2, D-ribulose and D-xylulose. And there is also N form of them. In 6 carbon, we only have 4 of them, D-cyclose, D-fructose, D-sorbose, and D-talose. Now, let's look at monosaccharide. Oh, we already, this is just, okay, on the basis of, we've already explained on the basis of functional group, ketones, and the aldosis. And we made mention that because of the presence of ketone as a functional group, for this one, the presence of aldehydes as the functional group. Already explained that. So in the case of disaccharide, is when you have 2 sugar molecules, where we have a condensation product of 2 sugar molecules, where 2 sugar molecules comes together through what we call a glycosidic bond to form disaccharide, meaning 2 sugar molecules linked together to form a disaccharide. The most common one is number 1, lactose. Lactose, which is found in milk. We have glucose plus fructose, which form what we call sucrose, and this is the sugar formed during photosynthesis. We have glucose plus another glucose from what we call maltose. So we are going to see how this the disaccharide is formed, the structure of the molecules. I think in the next study session or later. And we will say 1 or 2 things about them. While in the case of oligosaccharide, we have more than 2 sugar coming together through what we call the glycosidic bond. Starting from 3, we have trisaccharide, when we have 3, we have tetrasaccharide, pentasaccharide, up to 3. In most cases, oligosaccharides, we don't see them so common. They are mostly found in the form of recognition molecules on the surface of the membrane. We mentioned glycoproteins and glycolipids in our previous class. We have seen the structural or the membrane protein or the membrane lipids, where we say carbohydrate can be attached to the protein on the surface of the membrane. So most of those proteins that were, carbohydrates that are added to the membrane proteins and the membrane lipids to give glycoproteins or glycolipids are actually in form of oligosaccharides. Sugar molecules, the units are not up to 10 to 12. We made a mention how these glycoproteins play important role in termination of blood group. So, polysaccharide. Sorry, I put the glycose aminoglycans here. So let's take a here. Glycose aminoglycans, carbohydrates, polysaccharide. So in polysaccharide, when we have more than 10 sugar residues, 10 up to millions of them, they are called polysaccharides. And these polysaccharides are classified into homopolysaccharide when you have the sugar molecules are the same. When you have the same sugar molecule linked together to form a polysaccharide, for example, the glucose, all the glucose, all the sugars, many up to millions of glucose linked together, give what we call homopolysaccharide, the same sugar molecules. Example of them, we have starch, glycogen, cellulose, chitin, and we see the difference. And we have heteropolysaccharide, which are example agar, glycosaminoglycans, etc. Also simplified. And they can also be structural in terms of function or storage polysaccharide, which we will, I think, discuss in the next study session. Okay, now structure of glucose. Now, this is the structure of glucose. A 6-carbon molecule. It can either be in a linear form, which is the Fischer projection formula. And this molecule, as it is, although it represents some chemical properties of the glucose, but in solution in most cases, the carbonyl group can react with any of the alcohol group here. But mostly it doesn't react with the one very close to it because of steric hindrance. So it can easily react with the one at carbon 5 or the one at carbon 4, easily, to form the cyclic structure. This is what we call the Howard production formula. And this Howard production formula mostly is more thermodynamically stable, but even in solution, you can have the open chain as well as the cyclic chain. So under the physiological condition, the structure usually exists in either, doesn't exist as planar form as it is in the Howard production formula, but predicted to exist either in form of chair or both conformations. You can see the chair conformation. So we will discuss how this cyclization reaction takes place in subsequent systems. Isomerism. Isomerism. What is isomerism? A process by which a compound with some molecular formula will have different structural form. And this isomerism is, I just explained that it's actually due to the presence of this asymmetric carbon, which we call carbon. The most important one is the D and L. We've already explained why the D and L, how does it. And we cite the D and L orientation in sugar, although I didn't explain why the D and L in the because, for example, in the glucose, I only explained in glyceraldehyde. In glucose, we have many of them, the OH at carbon 2, carbon 3, carbon 4, carbon 5, which they can all determine the DL. But that actually is that the orientation of this OH group around the carbon atom adjacent to the terminal primary alcohol or alcohol carbon determine whether the sugar belongs to it. So which one is the terminal primary alcohol carbon? The terminal primary alcohol carbon is a carbon 6 here. So the last carbon, if it is a pipe carbon sugar, is going to be carbon 5. So what will determine is carbon 4. So the one adjacent to it, which is carbon 4 in the case of 5 carbon. While here we're talking about 6 carbon. So the one adjacent to the terminal primary alcohol is going to be carbon 5. So the carbon 5, the orientation of carbon 5 now determined. So when you look at the structure here, the carbon 5, you have the D sugar and you have the L sugar, and the difference is at 75. So when the orientation, when the OH group on this is on the right, it is D isomer. But when it is on the left, it is L isomer. And we mentioned that most of the naturally occurring monosaccharides are in D isoform, because the enzyme responsible for the metabolism has specific for this configuration. Another thing I need to mention, I think, with regard to this is the optical activity. That the presence of these asymmetric atoms confers would give a compound what we call the optical activity. What is this optical activity? The optical activity, when you have a sugar solution, and this sugar solution, for example, the sugar glucose solution, and this glucose solution was able to rotate a beam of polarized light to either left or right. There are some sugar molecules that when you subjected them to a beam of light, they can rotate that light to either left or right. It doesn't matter if maybe the sugar is in D, like it is going to be this side, or rather, no. The D solution, sugar solution of D glucose can rotate it to left. And if it rotated to left, it is laboratory. But if it rotated to right, it is dextrorotatory. So you can have a D glucose, but it can be in bracket D. If it is left, it will be negative. D negative meaning D laboratory. So sometimes even it's confused people whether D means dextrorotatory or L means laboratory. No, the D and L. D positive meaning D dextrorotatory. D negative means D laboratory. And I think this is, so you can have D positive, D negative. You can have L positive or L negative, depending on the rotation of this beam of light. So glucose solution is dextrorotatory. It rotates the beam of polarized light towards right. In fact, this is one of the reasons why they referred to glucose solution as dextrose in clinical terminology. Dextrose solution, why you call it dextrose is simply because of this phenomenon. And so, what are epimers? They are compounds that differ in the configuration in a particular carbon atom. For example, we have example of mannose, glucose, and galactose. When you look at the structure of these compounds, you'll find out that they only differ in one particular carbon. For example, between glucose and mannose, they are carbon-2 epimers. Glucose and galactose, they are carbon-4 epimers. They only differ around this carbon atom. So the cyclization, before we explain the cyclization, what is important to look at? What happened in the case of cyclization? For this cyclization to occur, first of all, we have two functional groups in, for example, the glucose or in all the sugars, for example. Either it's an aldehyde or a ketone, or aldosis or a ketosis. In aldosis, we have an aldehyde and alcohol functional group. So there is possibility of this carbonyl group and hydroxyl group to react. When they react, let's look at this structure. We can see this is an aldehyde group, this is an alcohol group. In a solution, they can actually react. In the solution, this OH group will have somehow to dissociate, it will have something partially negative. Or rather, we can have this hydrogen forming partially negative, positive, while this will have a partially positive, the oxygen will have a partially. Also, this bond can become one, so that you can have this oxygen forming a partial negative, while this carbon will have a partial positive. So if this happens, we can see that this oxygen can easily be attracted here. So this can lead to the breakage of this bond. So once this bond is broken, then another bond can form between this carbon and the oxygen here, leading to formation of what you call hemiacetal. So this is exactly what's happened in the case of cyclization. It's from hemiacetal. And also in the case of ketone, this is what happened. But still, the reaction can continue to form acetal. But this is not because of the still availability of this OH group available can actually influence the formation and you can have an acetal group. So also in the case of ketone, you can have a ketal group. So we'll see how this happens. So this is exactly what happened here. When the reaction, this carbon 1 can bend to carbon. I said the carbon 5, easily the OH group at carbon 5, and this is the OH group at carbon 5, that can easily form this or this. We'll talk about anomers. I think this is why I decided to do this one here. But before then, when the cyclization happens, two things can happen. When they form this structure, they can either form a 5-member ring atom or a 6-member ring atom. And when they form a 6-member ring atom, they assume the structure of the compound we call furan. So it look like the compound furan, and when it's from a 5 carbon, it look like the compound called furan. So when it is furan, it's from a furan ring. We call it furanous. It is furan. It is furanous. Glucose in solution mostly can either conform can form either the 6-atom ring or the 5-atom ring. So it can either form the furan ring or the furan ring. But in most cases, up to about 99%, it exists in form of furanous ring instead of furanous ring. So when it's formed a furanous ring, it is called glucopyranose. When it's formed a furanous ring, it is glucopyranose. So we say it mostly from furanous ring. Likewise, in the case of ketose, it's also like fructose, the most common one. The solution also mostly form the furanous ring instead of the furanous ring. So you can still have fructopyranose or fructofuranose. That should be fructofuranose is the most predominant and the most stable form. That is why we have a representative structure of furanose and glucopyranose. Now, another thing we need to explain here is that this formation of hemiacetal and hemiketal lead to formation of another chiral center. So initially, you can see carbon 1 is the carbonyl carbon or the keto carbon, and it is not a chiral center. But after the formation of the cyclization, it forms a chiral or isometric carbon we call it anomeric carbon. So the position of the OH group around the anomeric carbon now determine whether a sugar is called an alpha or a beta conformation. So we have an anomer. We have an anomer. Is another form of isomerism, which will determine sugar being an alpha or a beta. Apart from the D-glucopyranols, the D-glucopyranols can also be alpha or beta, depending on the orientation of the OH group. When the OH group is down on the anomeric carbon, it is called alpha. When it is up, it is called beta. So this is basically about the chemistry of carbohydrates, the sugar. So in the next class, we will be discussing still on disaccharides, polysaccharides, their examples. So you go through this. If you have any question, please do not hesitate so that we can discuss. I will try and link this output to the university teaching facility so that the discussion can continue. For those of us that doesn't want to communicate the way we communicate through WhatsApp, so we can be able to communicate. Thank you.